I work inside of a big company that has lots of not invented here going on, and I have very little experience with open source anymore, which I'm really sad about. But the upshot is I've really lost touch with what's going on in the community. So I'm like, I don't know what I'm going to talk about. But then I read this a couple of years ago, and this totally validated my thoughts, which was that I don't think open source monitoring tools have yet done this. So this quote from this guy who I eventually met at PuppetConf was like, you know what, instead of just alerting on the results of checks, basically, we should record the data and then do some analysis on the data and then alert on that. And I'm like, that's exactly what I want to talk about. So monitoring systems right now, we're very good at taking measurements and recording those measurements. We have tools like Graphite and CollectD that store time series data. We have Nagios' performance data extension that writes into those databases. And we have, what am I talking about there? Let's skip that. But anyway, the current state of the monitoring is that we have stuff that does alerting, but it's doing black box checking. And then we have stuff that's taking instrumentation data out of applications and putting them into time series databases. Black box monitoring is, oh, here we go. Here's a diagram. There's a network monitoring system unnamed that performs checks against a bunch of targets and maybe the alert fires directly from that check, you see. Perf data gets stored either directly scraped from the targets or from the network monitoring system into an external third-party database. But nothing is happening to that. When I talk about black box, I mean we're treating the system as a black box. We're poking it in the interface that we've exposed. We're acting against it as a user would act against it and trying to emulate the user experience. Whereas Whitebox is where we look inside the system itself and try and pull out all of the telemetry data from that system. So tools like Graphite allow us to do this. And kind of things I'm talking about that have real-world examples, with black box monitoring is a fuel indicator light on your car dashboard, whereas the tachometer is actually telling you how fast the engine is rotating at any point in time. So what's wrong with black box is that it's only really a Boolean expression. You get to say whether the test passed or not, which is fine. But it doesn't really tell you why sites are slow or why the image serving has stopped working, for example. That particular backend has stopped. I don't know why. It doesn't give us any predictive capability, how much capacity we have left in the system before we need to buy a new server. More problems with this check and alert model is that it doesn't really scale well. Every time we, it doesn't scale well for maintenance costs and resource costs. Even if you've written tools to automate your Nagios configuration, you still have the cost of adding new metrics to existing check scripts, or you want to add a new invocation of a script, or you want to modify thresholds to have different values on different classes of servers. It's all a non-trivial amount of work, and along with that, that work comes an added risk every time you have to make a specific change to the system. Let's not forget that every extra check we add incurs a physical cost on the monitoring infrastructure. And I know lots of you have done Nagios scaling, where you have proxies of proxies to be able to run all of the checks required in the check loop without overloading the system. So really the core of it is that the monitoring infrastructure, so monitoring sucks right now because the amount of work required to maintain your monitoring system doesn't scale sublinearly with the growth of your systems and the number of engineers you have. Or TLDR, if you take nothing away from this talk, take this away. Monitoring sucks because it's too hard. So anyway, I can point with a pointer, thanks. Awesome. So alerting based on time series data is potentially a way we can scale monitoring systems to large scale systems. So instead of having, if you can remember the model I drew previously, perhaps I can just skip back. Here we are. Individual checks probing individual systems and then reporting back to the master process. We have one process that does collecting from a whole bunch of things and aggregates all of that information in a time series database, and then another component which is sort of I can't think of the right word, separated responsibility for the collection and the testing to see whether things pass or not into a separate engine. And perhaps that separate engine no longer treats individual values as discrete elements, but can think about them in aggregate terms. And I mean, well, I'm going to talk more about this in just a moment, but I mean where you take sums of things across a whole cluster, or you take the average of things, or you look across a single host's recent history to say, is there a trend occurring that we need to care about? Now I've put that slide in, except I totally just explained what the what was. So anyway, let's move on. When I say time series, what I'm talking about is a stream of variables with little delta t offsets. Perhaps we're scraping at every interval of delta t, and we record a value in time. In the vertical axis, we're talking about the time, and across the horizontal axis, we're talking about different elements, or the ensemble axis of a series of machines in a cluster. Now, I don't have any audio, so this part is only going to suck, but if I can just narrate for you, this is, if you're familiar with The Simpsons, I hope most of you are, there's an episode, a scene where Barney and Homer and a bunch of the other guys are playing poker, and Barney becomes worried about the beer supply. And he says, I'm worried about the beer supply, because after this case and the next case, there's only one case left. So obviously, Barney is a very simple check and alert model, where if the number of cases of beer -1 is less than or equal to 1, then Barney becomes worried. All right, so we can see over time, it looks like this. So what I'm saying is this is a very traditional alert where we have a threshold and we can just check and point in time, is Barney worried or not? And after some point t, then yes, he is, and previous to that, he wasn't. And hopefully at some point, Homer goes to buy more beer, and then he becomes no longer unhappy. But this doesn't really scale to a lot of classes of alerts. For example, disks now are big, and when you set a threshold for free space on a disk, what do you set it to? Because now 10% of a disk is a lot of disk still. Do you really need to care that you've only got 200 megabytes free? Yes. 200 gigabytes free? But do we want to alert on absolute space? And it kind of depends on the application you have, because maybe 500 megabytes of free space is about normal, because your staging area for backups is supposed to stay about as much full as it can, with only a little bit of room as the stuff gets spooled off to tape and new stuff gets written in. Like, this might be a totally normal operating procedure. So you can't really use this threshold alert across the board. You need to set different priorities for different systems. Sorry, not priorities, different thresholds. So what's more interesting is how long until a disk is full, and is that time remaining sufficient for me to go to the shop and buy a new hard disk? So this is a segment from Speed, and it is where Dennis Hopper's character calls up Keanu and says, hey man, there's a bomb on the bus. Now I kind of wish I had the audio because I don't really remember the full quote, but it's, there's a bomb on the bus. If the speed drops below 50, the bomb explodes. Pop quiz, what do you do? And the Keanu says, well, I really want to know what bus it is. So anyway, this is kind of what Dennis Hopper's alert looks like. He really cares when the bus starts going above 50 miles an hour, at which point the bomb is armed. So if then the bomb is armed and then the speed drops below 50, the plot line is continued. So what we're looking at here is a rate of change of things over time. Speed being obviously well, let's not get into that, I'll talk about it in just a moment. But bomb armed, here we're setting a condition that we can then refer to in other alerts and use that to trigger whether or not another thing happens. Keanu's alert is if the speed is greater than or equal to 50 miles an hour, we should start saving the bus, right? What he actually cares about is when the bus starts to slow down, because that's when time is no longer on his side. As long as the bus is still going over 50 miles an hour, he's got all the time in the world to find and save the bus, right? So what Keanu really needs to know about is, like, when his pages should be going off is at the point when the bus starts slowing down. So what we need to do is look at the inflection point of the velocity of the bus, right? Which is acceleration when it crosses the zero line. You all remember your high school mathematics, right? So at the point between the derivative crossing 0, that's when the alert should fire. So this is kind of what I'm getting at, is the velocity minus some threshold divided by the acceleration is less than the time it takes to save the bus or fix a disk. Now it's time to start going to the shops and buying a hard disk or saving a bus. So this is kind of the first idea I want to talk about, is that calculating the rate of change of time series is a way that we can start manipulating this time series data to give us more useful, actionable alerts. So let's just spell it out in really plain terms. And we take a counter, which is the number of errors occurring over time, and we take the derivative of that, and then we can say, has the derivative of this counter crossed a threshold or not, in which case we're serving more errors than we expected to. I just realized I should have made a point that maybe your application is always serving errors at some point, and do you really want to know that it's greater than 0 all the time? Because like big applications tend to have errors, and there's probably a baseline error rate, I assume, because there are bugs all the time. So you want to threat this, you don't?
Day, like as a constant?
Yeah. So if you want to set that your errors are non-zero, it's kind of bad, but you want to set that the rate of errors is greater than your expected baseline of errors, and that's probably okay. So just discrete time series, as we talked about before, being individual elements, we don't actually have to do real calculus anymore. We can just take the difference between the most recent points and divide it by the time difference between them, and that's the rate, instantaneous rate and point of time. So if we run this calculation every time we do a new collection, then we've got the rate of change of each of these counter variables. So the second tip is to observe the history of an individual time series to gain some context about it. So let's say that this is the rate of errors, and it's just started alerting because it's crossed the threshold. Which of these two is worth getting out of bed for? I would say the really short spike is probably not worth paging me at 3 in the morning for. The slightly longer spike, it's probably not worth paging me at 3 in the morning for. But that's only because I'm a bastard and we almost live the, anyway. We're talking about the duration of the abnormality. Does this exist for a long period of time? Is this likely to continue, or has it fixed itself? In which case, yeah, there was a problem. Maybe I can look at it in the morning because it's not currently breaking any user experience. We've logged the fact that maybe we've logged the fact that this did happen, so we can go back and look at our logs and go, yes, maybe we can understand why that happened. But we shouldn't page anyone because it's not actually hurting anyone anymore. Thirdly, counters are much more useful to export from an application than gauge types, and I mean counters that always monotonically increase, whereas a gauge is something that changes value up and down over time. I guess everything else not monotonic. The reason is because if we're sampling data points, then it's possible for you to miss dips in the curve when a gauge is being measured, whereas a counter, you can guarantee that the value has only ever increased. So we can see that the sampling points of this particular counter has increased, and we can figure out what the rate of change of it is, more or less. This gauge, on the other hand, you'll never get the fact that we spiked to quite high levels early on. So it's better to export the data in counter type rather than gauge type, and that's just kind of an implementation detail that I wanted to cover. The next thing is that aggregating to each grouping level within your system gives you more and more information about the behavior of the system as a whole rather than individual components. So if you have a cluster of machines and they are doing so many queries per second, you want to know how many queries per second is the entire cluster doing. Well, that's very simple. You add them together and then you take the rate of that. I just really said that, didn't I? So anyway, we can move on. Ratios of rates. Oh yeah. When we talked about errors earlier, and we said errors exceeding some threshold might be something interesting to alert on, what happens if the number of queries has also gone up at that same point of time? Maybe that error threshold being exceeded isn't actually relevant anymore because it's still a fraction of a % of the total number of queries being served. So instead, how about take the rate of errors versus the rate of queries, and if that exceeds a percentage threshold, then it's time to fire an alert. And this means that we get to apply historical analysis or point-in-time analysis of comparisons of variables to decide whether or not we want to fire alert rather than hard coding a particular threshold. Okay, so what to alert on? Rate of change of QPS outside of normal behavior, ratio of errors to actual queries. We want to look at the latency, perhaps median latency, 95th percentile latency to understand what the tail is doing. Perhaps you have an SLO based on the latency, in which case you want to have something that says for 95% of the time we're going to be serving our queries faster than something. Bandwidth is also very important. Thank you. But really whatever is important to the business, which means figuring out with your boss or your CEO or perhaps yourself with what you actually care about, what your users care about, what you're selling to them, and then translating that back into something that you can measure. When to alert only if you can get somebody to do about it and it's affecting your business, right? If you alert somebody and they can do nothing about it because it's gone away, it's not documented, it doesn't make any sense, make sure that the alert is actionable, document it, and if you don't document it, 3 months from now, you're going to kick yourself. But despite all of this, I still think black box testing is necessary because time series-based alerting is something that you can't attain 100% coverage with. At the end of the day, the black box is still your last line of resort to make sure the service is still up. Now, it's possible for you to write all of the rules in the world that can make sure that your system is serving queries, hasn't served as many errors, but once you start to getting a complex system, the interplay of all these things is such that it's entirely possible to miss things. So I'm not going to say don't use Blackbox. Do use it, but in moderation. You should only need to test the bare minimum of the service. So anyway, if you didn't listen to anything I just talked about, do maths. Computers will help you with that. Counters instead of gauges, and derive the rates instead of exporting rates themselves. Compare them to one another because that's really interesting. And do historical analysis. I don't think I have any time for a demo, but that's okay. I was just going to demonstrate how awful R is. But say you would like to do this at home for yourself. Very simply, instrument your code with taking measurements of things. Say the query came in and I start the clock, and I send the query and I stop the clock, and then I add that to some map of times and number of how long I spent in that query, and export that. Every time you get an error, export that. And then aggregate it somewhere. Thank you. NumPy, I don't know. This is the part where I say the tools don't exist yet. The ideas are there. Some bright spark in the audience perhaps has the ingenuity to write such a tool and give it to the world. Wouldn't that be awesome? I do have demo code up at GitHub, which you can download and see what I was about to demonstrate, except it didn't. So if you have any questions, feel free to throw them at me. Yes, sir?
I was very interested when you put up the architecture diagram because it describes the product that exists.
This is more of an inspirational talk where I say, wouldn't it be nice if we were off somewhere in the future? But yes. The other, I do have an architectural diagram.
Yeah. No, I mean, you describe something that I know about that exists.
Oh, do you have a name for that thing?
Have you looked at a software called Performance Copilot?
I have not.
It's crufty, but it looks like that.
This sounds like an excellent starting point for making it less crufty. So Performance Copilot, is that right?
Yeah.
Performance Copilot, okay.